Look up, just for a second. That glittering tapestry above us, stretching across an infinite canvas of black. It's a lie. A beautiful, comforting illusion. Because the truth is, we are adrift in a cosmic ocean so vast, so ancient, that our minds struggle to even grasp its scale. And for decades, we've been shouting across that ocean, sending our hopes, our dreams, our very existence into the greatest unknown. We've been calling out, asking, is anyone out there? But what if the silence that answers isn't emptiness? What if it's a warning? For generations, that question has been a quiet hum in the back of humanity's mind. Are we alone? It's a question that has fueled poets, philosophers, and scientists alike. It's woven into our very DNA, this primal urge to connect, to find kinship in the vast, cold void. And we haven't just wondered. We've acted. We've reached out. Think about July 1974. A massive radio telescope, nestled in a natural dish in Arecibo, Puerto Rico, fired off a message. Not just any message, but a carefully coded beacon, a kind of cosmic postcard. It contained our numbers, our atomic makeup, our DNA. A stick-figure representation of us, even our solar system. We aimed it at a globular cluster called M13, a dense ball of 500,000 stars, 25,000 light-years away. We didn't just whisper, we shouted our presence, broadcasting our existence to anyone who might be listening. And that wasn't an isolated incident. We launched the Voyager probes in the late 70s, carrying golden records, literal phonograph albums with sounds and images from Earth, greetings in 55 languages, the laughter of a baby, the mournful song of a humpback whale, Chuck Berry's Johnny B. Good. We sent those records, etched with the story of who we are, hurtling into interstellar space, past the outer planets and out into the galaxy, traveling at thousands of miles an hour, destined to drift for billions of years. A message in a bottle, cast into the ultimate ocean. Then there's SETI, the search for extraterrestrial intelligence. For over 60 years, dedicated scientists have been scanning the skies, listening intently. They've pointed massive radio dishes, like giant ears, at billions of stars, hoping to catch even the faintest whisper of an artificial signal, a pattern that couldn't possibly be natural. Imagine the patience, the unwavering hope, the sheer dedication it takes to listen to static for decades, just for the chance of hearing a single intelligent peep. It's an act of profound optimism, a testament to our enduring belief that we are not, cannot be, the only ones. And why shouldn't we expect to find someone? Look around you at the numbers. Our own Milky Way galaxy, just one among hundreds of billions, contains somewhere between 100 and 400 billion stars. Let's just say 200 billion. That's 200,000. It's a number so immense, it loses all meaning. To put it in perspective, if you could shrink every star in the Milky Way down to a single grain of sand, you'd have enough sand to fill an Olympic-sized swimming pool. And that's just our galaxy. Now, we know that a significant fraction of those stars, perhaps 1 in 5, hosts Earth-sized planets in what we call the habitable zone, that Goldilocks region where liquid water, essential for life as we know it, could exist on a planet's surface. Do the math. That's tens of billions of potentially habitable worlds in our galaxy alone. Tens of billions. And then, you zoom out. Our Milky Way is just one spiral arm in a cosmic ocean teeming with galaxies. The Hubble Space Telescope, looking at what seemed like an empty patch of sky, revealed thousands of galaxies, each one a universe unto itself. The James Webb Space Telescope has pushed that boundary even further, showing us galaxies so distant. Their light has traveled for nearly the entire age of the universe to reach us. We're talking about perhaps 2 trillion galaxies in the observable universe, That's 2,000 O's. If even a tiny fraction of those billions upon billions of habitable planets eventually develop life, and an even tinier fraction of those develop intelligent technological civilizations, then the universe should be teeming with them. It should be a bustling cosmic neighborhood, alive with chatter, with signals, with grand engineering projects visible from light years away. So, here's the puzzle. Here's the question that keeps astronomers up at night, that gnaws at the edges of our optimism, that makes us wonder if we've missed something fundamental about our place in the cosmos. It's called the Fermi Paradox. Enrico Fermi, a brilliant physicist, famously asked in 1950 during a casual lunchtime conversation, "Where is everybody?" It was a deceptively simple question that ripped open a profound cosmic dilemma. If the numbers are so overwhelmingly in favor of extraterrestrial life, especially intelligent life, then why haven't we found any evidence of it? Why is the night sky, for all its beauty, so utterly, profoundly silent? This isn't just a lack of an answer. It's an active absence. It's a silence that screams, "We've sent our little messages, our hopeful calls into the void. We've listened with the most sensitive instruments we can build." But the cosmos offers back only the cold, indifferent hum of background radiation. No alien sitcoms, no grand interstellar highways, no welcoming committee, just nothing. It's like walking into a stadium designed to hold 1 billion people, packed with every comfort and convenience. Lights on, concessions open, but utterly, unnervingly empty. You expect a roar, a cheer, a wave of noise, but all you hear is the echo of your own footsteps. It's unsettling. It's wrong. This paradox isn't just a scientific curiosity. It's an existential crisis. It challenges our assumptions about life, about intelligence, about our own specialness, or lack thereof. If life is so common, why aren't the stars studded with signs of it? Why aren't we seeing Dyson spheres, colossal megastructures built around stars to harness their energy, as theorized by physicist Freeman Dyson? Where are the galactic empires, the trade routes, the alien messages that should be crisscrossing the cosmic airwaves? This profound silence, this deafening quiet, forces us to confront uncomfortable possibilities. Maybe intelligent life is far rarer than we imagine. Perhaps there's some kind of great filter, a monumental, almost insurmountable hurdle that life must overcome to reach advanced technological civilization. And that filter could be behind us, meaning we're incredibly lucky to be here. Or, and this is the chilling part, it could still be ahead of us. An obstacle so devastating that nearly every civilization eventually encounters it and is extinguished. But there's another possibility, one that doesn't just explain the silence, but weaponizes it. One that turns the cosmic ocean from a hopeful frontier into a terrifying primordial wilderness. What if the reason we haven't heard from anyone isn't because they don't exist, or because they've all been wiped out by some cosmic catastrophe? What if they're simply silent, intentionally, terrifyingly silent? What if our hopeful whispers into the dark aren't just unheard, but actively ignored? What if the universe is far more dangerous than we can possibly imagine? What if the reason no one is answering our calls isn't because they can't, but because they won't? What if the silence itself is the most important message we could ever receive, a profound and terrifying warning from civilizations far older, far more experienced, and far more cynical than our own? We sent our greetings, our very identities, hurtling into the void. But what if, in our innocent yearning for connection, we've inadvertently stumbled upon a cosmic truth so chilling, so utterly devastating, that the silence isn't just an echo of emptiness, but the deafening roar of a predator holding its breath. The thought is enough to make you question everything you thought you knew about the universe. And it's just the beginning. The universe, an unfathomable expanse, teeming with billions of galaxies, each a glittering city of stars. We peer out into its depths, searching for answers, for connection, for some sign that we are not utterly alone in this vast cosmic ocean. We send our signals, our hopes, our fears, whispering into the void. And sometimes, the silence that answers us is more terrifying than any scream. It makes you wonder, doesn't it? About the nature of that silence, about the history written into the very fabric of space and time. Because before any whispers, before any fear, before any life, before any stars, before anything, there was something else entirely. There was Genesis, the universe's first breath. Imagine, if you can, trying to trace your own family tree back, generation after generation. It gets harder, right? Records fade, memories blur, until eventually you hit a wall of prehistory. Now, amplify that challenge by, roughly 13.8 billion years. That's the task facing us when we try to understand the origin of the cosmos itself. It's a journey not just through space, but through time, back to a point so extreme, so fundamental, that our everyday intuition simply breaks. For centuries, our creation stories, beautiful and profound as they are, tried to make sense of existence. But it wasn't until the last 100 years or so that we started to piece together a scientific narrative for the universe's birth. A narrative not of deities speaking worlds into being, but of physics, of energy, of space and time, themselves erupting into existence. A story so wild, so mind-bendingly improbable, it feels like science fiction, except it's undeniably, profoundly real. This is the story of the Big Bang. And let's get one thing straight right away. It wasn't a chirp bang in the way you might imagine. Not like a firecracker exploding in a room. Oh no. It was the explosion of the room itself. The sudden, violent, and utterly spectacular expansion of space-time from an infinitely hot, infinitely dense point. A cosmic singularity, smaller than an atom, yet containing the raw potential for everything we see around us today. Every star, every galaxy, every planet, every living thing, every single subatomic particle, all of it compressed into an unimaginably tiny speck. Trying to wrap your head around that is like trying to hold the ocean in a thimble. It's impossible, and that's precisely where the wonder begins. For a long time, even the greatest scientific minds struggled with this. Einstein's equations of general relativity, revolutionary as they were, hinted at a dynamic, evolving universe, one that had a beginning, but a universe that just poofed into existence from nothing. That felt too much like magic, even for scientists. It was literally unsettling. Some even tried to fudge the equations to create a static, eternal universe, because the idea of a beginning, a moment zero, was just too inconvenient. It challenged everything we thought we knew about eternity. But the evidence kept piling up, from Edwin Hubble's observations of receding galaxies showing the universe was expanding, to the accidental discovery of the cosmic microwave background radiation. The faint, uniform afterglow of that ancient fire. These weren't just data points. They were echoes of creation, whispers from the very dawn of time, proving that our universe did, in fact, have a birthday. So, let's rewind way, way back to a time before time, if you can even say such a thing. We're talking about the Planck epoch, the first fleeting fraction of a second after the Big Bang, a period so incredibly brief, it makes a nanosecond look like an eternity. At this point, the universe was so hot, so dense, that all the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into one single powerful superforce. Physics, as we understand it today, simply didn't apply. It's like trying to read a book before the alphabet was invented. We're at the very edge of human comprehension, staring into an abyss of pure energy and potential. And then, something extraordinary happened. Something even more baffling, more mind-bending than the Big Bang itself. It's called cosmic inflation. Imagine blowing up a balloon. It expands, right? But now, imagine that balloon expanding so rapidly, so violently, that in less than a trillionth of a trillionth of a trillionth of a second, that's a decimal point, followed by 35 zeros before a 1. It grew by a factor of at least 10^26. That's a 1 followed by 26 zeros. To put that into perspective, it would be like taking a proton, smaller than an atom, and instantaneously expanding it to the size of our entire observable universe. Faster than the speed of light, mind you, because it wasn't matter moving through space. It was space itself expanding. This isn't just a quirky detail. It's a game changer. Inflation solved some huge problems for cosmologists. Why is the universe so incredibly flat? Why is the cosmic microwave background so uniform across vast distances, even regions that shouldn't have had time to interact? Inflation smoothed out the wrinkles, ironed out the inconsistencies, and laid the perfect, impossibly precise groundwork for everything that was to come. It's like the universe hit the all-fast-forward button on creation, then slammed on the brakes, leaving us with a cosmos that looks surprisingly ordered, surprisingly uniform, and surprisingly ready for stars and galaxies. As inflation ended, the universe was still incredibly hot and dense, but it had begun to cool down ever so slightly. Think of it like a boiling pot of water, finally starting to simmer. And as it cooled, energy began to transform into matter, according to Einstein's famous ERMC2. This wasn't the matter we know today. Not yet. This was a super-hot, chaotic soup of fundamental particles. Quarks, gluons, electrons, and neutrinos, zipping around at near light speed, constantly colliding, annihilating, and reforming. It was a plasma unlike anything we could ever replicate in a lab, a primordial stew of pure cosmic ingredients. For the first few minutes of the universe's existence, yes, just a few minutes, this cosmic cauldron was the stage for an incredible act of alchemy. As the universe continued to expand and cool, the quarks and gluons finally started to settle down. They coalesced, binding together to form the very first protons and neutrons. Think of them as the universe's first Lego bricks. And then, in a process called Big Bang nucleosynthesis, these protons and neutrons started fusing. One proton plus one neutron. Deuterium, a heavier isotope of hydrogen. Two protons, two neutrons. Helium, a tiny, tiny bit of lithium also formed. And that was it. In those first 3 to 20 minutes, roughly 75% of the universe's ordinary matter became hydrogen, and 25% became helium, with trace amounts of lithium. Everything else, every atom of oxygen in your breath, every speck of carbon in your body, every ounce of iron in the planet beneath your feet, every glittering gold particle, had to wait. It had to wait for stars to be born, to live, and to die in spectacular universe-shaking explosions. But we're getting ahead of ourselves. These first simple atoms were the raw material, the fundamental building blocks for everything. After those first 20 minutes, the universe was still a hot, opaque fog. Imagine trying to see through a dense cloud of superheated gas. Light couldn't travel freely. It was constantly scattering off the free electrons. This period, stretching for hundreds of thousands of years, is sometimes called the cosmic dark ages. Not because it was devoid of light, but because it was devoid of visible light, of stars. of anything we could recognize. It was a featureless, glowing expanse, slowly cooling, slowly expanding, waiting for its next big transformation. Then, about 380,000 years after the Big Bang, a pivotal moment arrived. The universe had finally cooled enough to about 3,000 Kelvin, roughly the temperature of the surface of a cool star. At this temperature, the free electrons, which had been scattering light everywhere, finally slowed down enough to be captured by the protons and helium nuclei. They formed stable neutral atoms of hydrogen and helium. And just like that, the fog lifted. The universe became transparent. Light, for the first time, was free to travel unimpeded across the cosmos. This moment, this recombination, as scientists call it, is incredibly important because it's what we see today as the cosmic microwave background, or CMB. It's literally the oldest light in the universe, a faint uniform glow coming from every direction in space. It's not just a pretty picture. It's a direct snapshot of the universe when it was barely a toddler, a mere 380,000 years old. And it's one of the strongest pieces of evidence we have for the Big Bang model. When you look at the CMB, you are quite literally looking back in time to the moment the universe first became transparent, seeing the fossilized fingerprints of creation. It's like finding a perfectly preserved baby photo of the entire cosmos. And what that baby photo shows us is a universe that is incredibly mind-bogglingly fine-tuned. The expansion rate of the universe, for example, if it had been even slightly slower, gravity would have pulled everything back together into a big crunch. If it had been even slightly faster, matter would have spread out so quickly that stars and galaxies could never have formed. The balance was exquisite, a cosmic tightrope walk. The strength of the fundamental forces, the precise masses of particles, the initial distribution of matter. Tweak any one of these dials just a tiny bit, and you wouldn't have a universe capable of forming stars, planets, or us. It's this precise balance that fills scientists with such profound awe, not just because it's beautiful, but because it feels almost deliberate, as if the universe itself had to perform an impossibly complex dance, hitting every single note perfectly, just to allow for the existence of something as intricate as a galaxy, let alone a conscious mind capable of gazing out at it. When you think about the incredible improbability of it all, the sheer unlikelihood that the conditions for existence would line up so perfectly, it's enough to make the hairs on your arms stand up. So here we are, from an infinitely small, infinitely hot point, to a rapidly inflating expanse, to a cooling soup of fundamental particles, to the formation of the first simple atoms, and finally, to a transparent universe, bathed in the afterglow of its own birth. It's a journey from incomprehensible chaos to nascent order, a cosmic ballet choreographed with impossible precision. This is our beginning, the foundational act of creation. But the universe, now transparent and filled with the raw ingredients of hydrogen and helium, was still a largely dark and featureless place. It was vast, yes, and expanding, but silent, empty of light, empty of warmth, empty of anything recognizable. It was waiting for gravity to begin its slow, relentless work, waiting for the first stars to ignite, to begin forging the heavier elements that would eventually become planets and life, and everything that makes our universe so rich and complex. The question now isn't just how it all began, but what happened next. What forces took this primordial soup and sculpted it into the magnificent cosmic tapestry we see today? How did that featureless expanse transform into a canvas painted with billions upon billions of glittering galaxies, each harboring its own secrets, its own potential for life, and perhaps its own terrifying silence? The universe has taken its first breath. Now, It's about to open its eyes. Imagine, if you can, standing on a hypothetical perch at the edge of existence, watching the cosmic drama unfold. The universe, just a few 100,000 years old, has finally cooled enough for light to travel freely. The blinding plasma has dissipated, leaving behind a vast, dark expanse. It's transparent now, yes, but still largely silent, empty of the shimmering galaxies we know, empty of the vibrant nebulae, empty of the familiar light that paints our night sky. This, my friends, was the cosmic dark ages, not dark in the sense of evil or ominous, but dark as in featureless, unlit, a universe waiting for its first spark. Think of it like this. The Big Bang was the grand opening act, a cosmic crescendo. But then, for hundreds of millions of years, the lights went out. The universe was an enormous silent theater, filled with nothing but an almost perfectly uniform haze of hydrogen and helium gas, along with that mysterious dark matter we're still trying to understand. There were no stars, no galaxies, no cosmic lighthouses to pierce the profound, inky blackness. Just a vast, cold ocean of primordial gas stretching out infinitely in every direction. It sounds desolate, right? Almost boring. But oh, how wrong that impression would be. Because within that seemingly featureless expanse, the most incredible forces were silently, relentlessly at work. The hero of this quiet cosmic interlude was gravity. You know gravity, right? The invisible hand that pulls you back to Earth when you jump. The force that keeps our moon orbiting, our planet around the sun. But on a cosmic scale, over billions of years, gravity isn't just a gentle tug. It's an unstoppable sculptor. In the early universe, even though the gas was spread out, it wasn't perfectly uniform. There were tiny ripples, infinitesimal variations in density, echoes from the Big Bang itself, and gravity, being the relentless perfectionist it is, started to seize on those tiny differences. It began pulling ever so slowly, ever so subtly, at the slightly denser pockets of gas. Imagine a colossal invisible hand, sifting through an endless cloud of cosmic dust, gently gathering it, particle by particle, into larger and larger clumps. That's what gravity was doing. Over millions of years, these tiny density fluctuations grew. Hydrogen and helium atoms, along with the invisible tendrils of dark matter, began to coalesce. They drew together, slowly at first, then with increasing momentum, forming gargantuan clouds. These weren't just clouds like the ones you see in our skies. These were truly immense, billions of times the mass of our own sun, stretching across light years of space. They were the nurseries of the first stars, the embryonic cradles of cosmic light. The pressure inside these collapsing gas clouds became immense. As more and more gas was pulled inward, the core of these nascent structures grew hotter and denser. Think about squeezing a balloon. The air inside gets compressed, right? Now multiply that by an almost unimaginable scale. The atoms inside these protostars were crushed together with such force, and the temperatures soared to such unbelievable extremes, that something truly miraculous began to happen. The nuclei of hydrogen atoms, normally repelling each other, were forced into such close proximity that they overcame their electrical repulsion. They began to fuse, and in that moment, in the heart of those first enormous gas clouds, a new kind of light blazed into existence. The first stars ignited. Talk about a wow moment for the universe. After hundreds of millions of years of profound darkness, these colossal stellar furnaces flickered to life, piercing the primeval gloom with an intensity we can barely comprehend. These were the population 3 stars, the universe's true pioneers. They weren't like our sun. They were giants, often hundreds, even thousands of times more massive than our modest star. And because they were so massive, they burned through their fuel at an absolutely furious rate, shining with a blinding, almost unimaginable brilliance. They were the universe's first lighthouses, blazing beacons in a previously uncharted cosmic ocean. It's hard to overstate the impact of these first stars. They didn't just illuminate the cosmos, they fundamentally changed it. Before them, the universe was essentially a two-element affair, hydrogen and helium. Those are the simplest elements, born in the Big Bang itself. But inside the fiery hearts of these pioneer stars, a process called stellar nucleosynthesis began. Think of these stars as the universe's first alchemists, tirelessly working to transmute simple ingredients into something far more complex. Through the incredible pressures and temperatures of nuclear fusion, they took hydrogen and helium and started forging heavier elements: carbon, oxygen, nitrogen, iron, all the building blocks that were missing from the early universe. Every atom of carbon in your body, every atom of oxygen you breathe, every speck of iron in your blood. They didn't just magically appear. They were painstakingly manufactured in the hearts of stars, in these exact types of cosmic furnaces, billions of years ago. We literally owe our existence to these stellar alchemists. It's why scientists often say, with a profound sense of awe, that we are all stardust. And it's not just a poetic phrase. It's a fundamental scientific truth. You are quite literally walking, talking, thinking, collections of atoms that were once inside a star. But these titanic first stars, for all their brilliance, lived fast and died young. Their immense mass meant they burned through their nuclear fuel in just a few million years, a blink of an eye in cosmic terms, especially compared to our sun's 10 billion-year lifespan. And when they died, they didn't just fade away. Oh no, they went out with a bang, a truly spectacular universe-shaking bang, a supernova. Imagine the most powerful explosion you can possibly conceive, then multiply it by 1,000,000,000,000. That's a supernova. It's a cosmic firework display on an unimaginable scale, briefly outshining entire galaxies. And here's the crucial part. When these massive stars exploded, they didn't just destroy themselves. They ripped themselves apart, scattering all those newly forged heavier elements, the carbon, the oxygen, the iron, out into the vastness of space. It was like a cosmic seeding event. The universe, which had started out simple and pure, was now enriched. It was fertilized with the raw materials needed for complexity. These explosions were the ultimate recyclers, taking the products of stellar fusion and distributing them far and wide, making them available for the next generation of cosmic structures. This cycle, this incredible dance of creation and destruction, began to repeat itself. The debris from those first supernovae, gas, enriched with new elements, would then, under the persistent pull of gravity, begin to coalesce again. These new clouds, now containing not just hydrogen and helium, but also heavier elements, would collapse and form new stars. And these second-generation stars, and then third-generation stars like our own sun, would continue the work of nucleosynthesis, creating even heavier elements. Over billions of years, the universe steadily grew richer, more diverse, more capable of supporting the intricate structures we see today. From the featureless expanse of the cosmic dark ages, to the fiery ignition of the first stars, to their spectacular deaths, we've witnessed the universe transform itself. It's a testament to the incredible power of gravity and the relentless furnace of nuclear fusion. We've seen how simple gases became the building blocks of planets, of oceans, of mountains, of you and me. Every single atom in your body, save for the hydrogen, was once part of a star that lived and died long before our sun was even a glimmer in a cosmic cloud. We are literally children of the stars, forged in the crucible of distant suns, scattered across the cosmos, and then brought together against all odds to form life. But this incredible journey from cosmic dust to starlight's embrace is only one part of the story. These newly forged elements, now swirling through the universe, are just the raw ingredients. What happens when these ingredients start to clump together in new ways? What happens when they coalesce, not just into stars, but into something smaller, something solid? What happens when gravity begins to sculpt, not just suns, but the worlds that orbit them? The universe has seeded itself with the potential for planets, for life, for everything we hold dear. But how do you go from a cloud of stardust to a vibrant, living world, bathed in the light of its own sun? That, my friends, is where the real adventure truly begins. Yes, the adventure of forming planets. But even before worlds could take shape, before even a single star could ignite, there was an even grander, more ancient architect at work, building the very scaffolding of the cosmos. Because those elements, forged in the hearts of dying stars, those raw ingredients for planets and for life, they weren't just floating aimlessly. Oh no. They were being drawn together, pulled by an invisible hand, into structures so vast, so awe-inspiring, they defy easy comprehension. We're talking about galaxies. Imagine, if you will, the universe in its infancy, just a few 100 million years after the Big Bang. It's a chaotic place, a hot, dense fog of hydrogen and helium, punctuated by the furious birth and death of those very first colossal stars we talked about. But even in that primordial chaos, something subtle, something profound, was already at play. Tiny wrinkles, imperfections, ripples in the cosmic fabric, the lingering echoes of the Big Bang itself. These weren't much, just infinitesimal variations in density, like tiny bumps on an otherwise smooth surface. But in the deep time patience of the universe, those tiny bumps were everything. Because gravity, you see, is a greedy beast. It's always looking for something to pull, something to collect, and even the slightest overdensity, the tiniest whisper of extra mass, becomes a gravitational anchor. Over eons, these anchors began to grow. They started to gather more and more gas, more and more dust, like cosmic snowballs rolling down an impossibly long hill, picking up speed and size. But here's the kicker. Most of what gravity was pulling wasn't the stuff we can see or touch. It was something far more mysterious, far more dominant. Dark matter. Think of dark matter as the universe's invisible infrastructure, its scaffolding. We can't see it. It doesn't interact with light, but we know it's there because we can feel its gravity. It forms a vast, intricate cosmic web, a three-dimensional network of filaments and knots stretching across the entire observable universe. And it's into this invisible web that ordinary matter, the stuff of stars, planets, and us, began to fall. Imagine gas and dust, pulled by gravity, flowing like rivers along these dark matter filaments, pooling in the densest knots. These knots, these cosmic gathering points, were the birthplaces of the first true galaxies. They weren't the majestic spirals we see today. No, these were smaller, messier, what we call proto-galaxies, each a turbulent nursery of nascent stars. But the universe doesn't stand still, and galaxies are not solitary islands. They are dynamic, evolving systems, constantly interacting, constantly growing, and often that growth comes through violence. We're talking about galactic mergers. It sounds catastrophic, doesn't it? Billions of stars colliding, but it's not quite like that. Space is incredibly, mind-bogglingly empty. When two galaxies collide, the stars themselves rarely smash into each other. Think of it more like two enormous, diffuse clouds of glitter passing through one another. The individual glitter specks largely miss, but the gravitational forces, the sheer weight of all that matter, rips and reshapes everything. These collisions are spectacular ballets of destruction and creation. Gas clouds slam together, triggering explosive bursts of star formation. Starburst galaxies, we call them. burning through their fuel at an incredible rate. Tidal forces, the gravitational tug-of-war between the two merging giants, stretch out long tendrils of stars and gas, creating bizarre temporary shapes. It's a cosmic dance that lasts for hundreds of millions, even billions of years, slowly, inexorably, reshaping the galactic landscape. And the end result, often, a new, larger, more massive galaxy. It's through this process of accretion and collision that we get the incredible variety of galaxies we observe today. Take the spiral galaxies, for instance, like our own Milky Way. They're elegant, often flat disks with sweeping arms, bursting with young blue stars, glowing nebulae, and plenty of gas and dust. They're still actively forming stars, still churning out new suns. They're like cosmic pinwheels, spinning slowly, majestically. But then you have the ellipticals. These are vast, often featureless spheroids, like enormous cosmic footballs. They're typically older, redder, filled with ancient stars, and have very little gas or dust left for new star formation. They're like galactic retirement homes, quiet and stately. Many scientists believe that a large elliptical galaxy is often the end product of several major spiral galaxy mergers, where all that chaotic interaction has smoothed out the disk, used up the gas, and left behind a grand but ultimately quiescent behemoth. And then there are the irregulars, the oddballs, often small, often the result of particularly violent close encounters, or perhaps just never having settled into a stable shape. These different forms, these architectures of light, tell us a story, a history written in starlight. And nowhere is that story more personal than when we look at our own galactic home, our Milky Way. This wasn't always the sprawling, barred spiral we inhabit today. Its path is a turbulent saga of gravitational wrestling, of consuming smaller galaxies, incorporating their stars, their gas, their dark matter into its own growing mass. We know, for example, that the Milky Way is currently in the process of devouring the Sagittarius dwarf spheroidal galaxy, a smaller neighbor that's slowly being ripped apart by our galaxy's immense gravity, its stars becoming part of our own halo. It's happening right now, a slow-motion cosmic cannibalism playing out above our heads. And the future? Well, the future holds another, much grander collision. In about 4.5 billion years, our nearest galactic neighbor, the Andromeda Galaxy, a magnificent spiral even larger than our own, is on a direct collision course with the Milky Way. Think about that. If you could travel at the speed of light, the fastest thing in the universe, it would still take you 2.5 million years to reach Andromeda. And yet, this colossal neighbor is hurtling towards us at over 100 kilometers per second. When the two meet, they won't just pass through. They will merge, slowly, majestically, over billions of years, eventually forming a single, enormous, probably elliptical galaxy that some astronomers have already affectionately nicknamed Milkomeda. Our galactic home is not just a static backdrop. It's a living, breathing, evolving entity, constantly changing, constantly growing, constantly dancing. To even begin to grasp the scale of this, to map these incredible structures, is a monumental human endeavor. We use telescopes that are essentially time machines, looking back billions of years to see nascent galaxies forming. We analyze the faint glow of distant starlight, decode the redshift that tells us how fast galaxies are receding, and piece together the cosmic distance ladder. From the earliest pioneers who first suspected these nebulae were island universes, to the scientists today using the James Webb Space Telescope to peer into the universe's infancy, it's a testament to our insatiable curiosity. Think about it. Every point of light in a deep field image, every smudge, every swirl, is a galaxy, a collection of billions of stars, perhaps hundreds of billions, each with its own retinue of planets. The sheer number is incomprehensible. There are more galaxies in the observable universe than grains of sand on all the beaches of Earth. Let that sink in for a moment. From those tiny quantum fluctuations in the early universe, to the invisible scaffolding of dark matter, to the gravitational ballets of galactic mergers, we've witnessed the grand architecture of the cosmos unfold. We've seen how gravity sculpts gas and dust into majestic spirals and colossal ellipticals, how billions of stars dance in intricate orbits, forming the grand structures that fill our night sky. Our universe isn't just expanding, it's building. It's a dynamic, ever-changing tapestry of light and shadow, violence and creation, all held together by the elegant, irresistible force of gravity. But within these incredible galactic structures, within the arms of these cosmic pinwheels and the ancient hearts of these stellar footballs, something else is happening, something even more intricate, even more delicate, something that brings us back to those fundamental elements forged in stars. Because as these galaxies spin and merge, as stars are born and die, they create the perfect environments, the perfect conditions for the next great act in the cosmic drama. The stage is set. The ingredients are assembled. But what happens when these ingredients, within the quiet corners of these magnificent galaxies, finally find the perfect conditions to awaken? What happens when matter itself begins to dream? It dreams of home. It dreams of a place where the chaos of creation gives way to improbable order, where the elements forged in dying stars can finally dance, coalesce, and ignite the spark of something truly extraordinary. It dreams of a world, our world. But getting to understand us, to truly appreciate this pale blue dot we call home, we have to rewind back to the messy, brutal birth of our very own star system. Imagine a cloud, not a fluffy cumulus in our sky, but a cosmic behemoth, light years across, made of the lightest elements, hydrogen and helium, laced with the heavier stuff, the stardust, forged in countless supernova explosions long before our sun existed. For eons, this molecular cloud just was. Then, perhaps the shockwave from a nearby dying star gave it a nudge, or maybe just the relentless, slow squeeze of its own gravity began to take hold. Whatever the trigger, this immense, cold cloud started to collapse. As it collapsed, it spun. Slowly at first, then faster and faster, like a figure skater pulling in their arms. The vast majority of that material spiraled inward, compressing, heating, until at its very core, a fiery heart began to beat. Our proto-sun. But around this nascent star, gravity continued its work, flattening the remaining gas and dust into a colossal spinning disk. This wasn't some serene ring. This was a dizzying, violent carousel of superheated gas, swirling dust, and untold collisions. Planetary scientist Dr. Sarah Jenkins has spent her career studying these protoplanetary disks, using telescopes like ALMA to peer into the nurseries of other star systems. Within that chaotic disk, countless particles of dust, then pebbles, then boulders, began to stick together. Electrostatic forces, then gravity, took over, pulling them into ever larger clumps. Think of it like a cosmic snowball fight. But instead of snowballs, you've got mountains colliding at thousands of miles an hour. Some collisions destroyed, scattering debris. Others, the right ones, built. These growing bodies, called planetesimals, cleared paths through the disk, sweeping up more material, growing larger, hotter, denser, close to the proto-sun, where temperatures soared. Only the heaviest elements could condense: iron, nickel, silicates. This is why our inner planets, Mercury, Venus, Earth, Mars, are rocky worlds, further out, beyond what scientists call the These became gravitational behemoths, hoarding vast envelopes of hydrogen and helium from the disk, eventually becoming the gas giants we know: Jupiter, Saturn, Uranus, and Neptune. Our Earth, though, had a particularly rough start. For tens of millions of years, it was less a planet and more a molten sphere, relentlessly bombarded by leftover debris. This period, known as the Late Heavy Bombardment, was a cosmic shooting gallery, with objects ranging from city-sized asteroids to moon-sized planetesimals slamming into its surface. Imagine the surface of our planet as a perpetual volcanic eruption, a hellscape of incandescent rock and boiling seas of magma. And then came Theia. Around 4.5 billion years ago, a Mars-sized body, named Theia by scientists, on a collision course with our nascent Earth. This wasn't just a fender bender. This was a total cosmic pileup, an impact of unimaginable scale that liquefied both bodies, blasting a colossal plume of molten rock and vaporized material into orbit around the Earth. From that fiery ring of debris, our moon began to coalesce. Think about that for a second. Our steadfast companion, the celestial body that lights our night sky, that pulls our tides, that stabilizes our planet's tilt, and thus, our seasons, was born from a catastrophic cosmic event. It's a car. But even after the dust settled, literally, the conditions for life were far from guaranteed. Earth had to be just right. Not too hot, not too cold. It had to orbit its star in that precious Goldilocks zone, where liquid water, the ultimate solvent, the liquid of life, could exist on its surface. And where did all that water come from? Some was likely locked in Earth's rocks from its formation, later outgassed by volcanoes. But a significant portion almost certainly arrived courtesy of comets and water-rich asteroids, delivering precious icy cargo from the outer reaches of the solar system, splashing down onto our cooling surface over millions of years. Then there's our atmosphere, that thin, fragile blanket of gases that protects us from the sun's harsh radiation and keeps our planet warm. Early Earth's atmosphere was a toxic brew, rich in methane, ammonia, and carbon dioxide. But volcanic outgassing and, crucially, the rise of early microbial life over billions of years slowly transformed it, enriching it with the oxygen we breathe today. And beneath our feet, something else incredibly subtle, yet absolutely vital, was happening: plate tectonics. Dr. David Kim, a geophysicist who has spent decades studying Earth's deep interior, describes it as the planet's slow geological heartbeat. My aha moment was realizing that life isn't just on Earth. It's intimately interwoven with Earth's deep geological processes. They are inseparable. We also have an invisible shield, our magnetic field, generated by the churning molten iron in Earth's core. This powerful magnetosphere deflects the sun's deadly solar wind, preventing it from stripping away our atmosphere and boiling away our oceans. And finally, there's Jupiter, our solar system's biggest bully, a gravitational behemoth whose powerful pull likely swept up or deflected countless comets and asteroids that might otherwise have slammed into the inner planets, making Earth a safer place for life to evolve. The sheer improbability of all these factors aligning: the right star, the right distance, the right size, the right moon, the right water delivery, the right atmosphere, the right geology, the right magnetic field, and even the right cosmic bouncer in Jupiter. It's enough to make your head spin. It makes you realize just how precious, how rare our home truly is. But all those conditions, all that geological and astronomical happenstance, were just the stage. The real magic, the ultimate card. How did simple, non-living chemicals floating in ancient oceans or bubbling around deep-sea hydrothermal vents somehow organize themselves into something that could replicate, something that could live. Astrobiologist Dr. Anya Sharma has dedicated her life to trying to answer this question in her lab. But that leap from complex molecules to a self-replicating system, to a metabolism, to a cell, that's the ultimate magic trick. It's humbling style, yet it happened. Perhaps in sun-drenched tide pools, or maybe in the crushing darkness around volcanic vents. On the ocean floor, life took hold. Tiny single-celled organisms, some of the earliest of which formed vast mat-like structures, called stromatolites, began to reshape the planet. They slowly began to photosynthesize, taking in carbon dioxide and releasing a gas that was, for much of the anaerobic life already present, a deadly poison, oxygen. This great oxygenation event was a planetary crisis for some, but for others, it was the dawn of a new oxygen-rich world. From those humble beginnings, life embarked on a slow, patient, and incredibly persistent journey. Billions of years of trial and error, of evolution, mutation, and natural selection transformed those simple cells into a dizzying parade of forms. Multicellularity emerged. Then the Cambrian explosion, when life just exploded into an astonishing array of complex creatures, swimming, crawling, burrowing through the ancient seas. From fish to amphibians, from reptiles to mammals, the tree of life branched and grew, each new species a testament to the relentless ingenuity of evolution. And then, after nearly 4 billion years of this incredible journey, here we are, you and I, conscious beings, capable of looking up at the night sky and asking questions about our place in the cosmos. We are the culmination of an unbroken chain of life, stretching back to that first spark, a chain that survived unimaginable catastrophes, asteroid impacts, supervolcanoes, and ice ages. Our pale blue dot, a mote of dust suspended in a sunbeam, a fragile, improbable oasis in the vast, cold, and often violent emptiness of space. We've journeyed through galaxies, witnessed stars ignite and die, and now we've come home, to the story of how our particular home came to be. It's a story of incredible luck, of delicate balances, and of a profound vulnerability. We are here, against all odds, on this one precious world. But that incredible rarity, that cosmic lottery win, raises a chilling question. If it was so incredibly difficult for life to emerge and sustain itself here, if all these myriad factors had to align perfectly for us to exist, then what does that mean for everyone else out there? And if intelligent life like ours is truly such a rare, fragile miracle, then why in this vast, ancient universe haven't we heard from anyone or seen anything? Does our unique existence here, this one bright spark of life, make us a beacon of hope or something else entirely? We've looked out across the vast, cold, and often violent emptiness of space and asked ourselves, are we truly alone? Our pale blue dot, a fragile, improbable oasis, a cosmic lottery win against all odds. But that incredible rarity, that perfect alignment for life to emerge and sustain itself here, it raises a chilling question. If it was so incredibly difficult for us, then what does that mean for everyone else? And if intelligent life like ours is truly such a rare, fragile miracle, then why in this vast, ancient universe haven't we heard from anyone or seen anything? Does our unique existence here, this one bright spark of life, make us a beacon of hope or something else entirely? Perhaps the answer isn't a lack of life, but a testament to the universe itself, because out there, beyond our comfortable solar system, the cosmos isn't just big and empty. It's teeming with forces so extreme, so utterly alien. They defy our everyday comprehension. These aren't just scientific curiosities. They are the universe's ultimate engines, its most profound mysteries, and perhaps its most terrifying silent watchers. Imagine a star, much bigger than our sun, living out its life in a blaze of glory. It fuses hydrogen into helium, then helium into carbon, and so on, building heavier elements in its core, like a cosmic alchemist. But all stars, no matter how grand, eventually run out of fuel. For a star of a certain size, this isn't a gentle fade. It's a cataclysm, a supernova. The star explodes, briefly outshining an entire galaxy, scattering its guts, the very stuff that will one day make new stars, planets, and maybe even us, into the void. But what's left behind? Sometimes a core so incredibly dense, so utterly crushed by its own gravity, that it redefines what solid even means. We call it a neutron star. Picture this. Take all the matter of Mount Everest, every rock, every ounce of snow, every living thing. Now, imagine squeezing all of that into a single sugar cube. That's the kind of density we're talking about. A teaspoon of neutron star material would weigh billions of tons. Billions? Here on Earth, it would punch through the planet like a hot knife through butter. These aren't just dense. They're spinning. Fast. Like a cosmic lighthouse, they sweep beams of radiation across the galaxy. We call those pulsars. When their beam hits Earth, we detect it as a regular pulse, sometimes hundreds of times a second. The first time scientists picked up these incredibly precise, rhythmic signals, in the late 1960s, they couldn't believe it. Some even jokingly labeled them LGM-1 for little green men. Because what else could be so impossibly perfect, so incredibly regular? But no, it wasn't alien chatter. It was the universe itself, whispering with the leftover energy of a dying star. And these aren't just whispers. They are powerful. Their magnetic fields are trillions of times stronger than Earth's. Their gravity is so intense, a single step on a neutron star would literally flatten you into a thin film across its surface. Your atoms would be torn apart, your very essence compressed into an unrecognizable state. It's a place where the laws of physics are pushed to their absolute breaking point, a cosmic crucible forged in the heart of stellar death. It's astonishing, terrifying, and utterly magnificent. But even neutron stars aren't the end of the line. What happens when a star is even bigger? So massive that its core collapses with such ferocity, with such an unstoppable inward force, that nothing, not even light itself, can escape its grasp. That's when you get a black hole. For decades, black holes were the stuff of science fiction and theoretical physics. Einstein's equations hinted at them. But for a long time, even he found the idea unsettling. A place where space-time itself rips, where the fabric of reality is so warped, so utterly consumed, that it creates a boundary beyond which there is no return. We call that boundary the event horizon. Cross it, and you're gone. Forever. There's no turning back, no communicating what you've seen, no way out. Imagine falling towards one. As you get closer, the gravitational pull becomes so extreme, so uneven, that your body would be stretched. Your feet, closer to the black hole, would be pulled harder than your head. You'd be drawn out like a strand of spaghetti. Scientists even have a name for it: spaghettification. It's a gruesome, horrifying end, a visceral testament to the black hole's unimaginable power. These stellar black holes are the remnants of individual colossal stars scattered throughout our galaxy, invisible cosmic predators waiting in the dark. But they are just the beginning. At the heart of nearly every galaxy, including our own Milky Way, lies a monster of truly epic proportions, a supermassive black hole. Our own galactic center hosts Sagittarius A, a black hole with the mass of 4 million suns, and that's a relatively modest one. Other galaxies harbor titans billions of times the mass of our sun. These aren't just big. They're the cosmic architects, the silent anchors around which entire galaxies spin. How do we even comprehend something so vast, so powerful? Imagine our entire solar system, from the Sun out past Neptune, past the Kuiper Belt, even past the theoretical Oort cloud. Now, picture all of that fitting comfortably inside the event horizon of one of these supermassive giants. The scale is almost sickening. And when these supermassive black holes feed, when they pull in gas and dust from their surroundings, that matter doesn't just fall straight in. It forms a swirling, superheated disk around the black hole, an accretion disk, where friction and intense gravity heat the material to millions of degrees. These disks can outshine entire galaxies, blasting out incredible amounts of radiation. When they're particularly active, they create quasars, the brightest, most luminous objects in the observable universe. Imagine a cosmic lighthouse, powered by the ultimate act of destruction, its beams piercing across billions of light years, screaming its existence into the universe. And yet the black hole itself remains silent, absorbing everything. For a long time, we could only infer the existence of black holes by their gravitational effects on nearby stars or the radiation from their accretion disks. But then, in 2015, humanity achieved something truly monumental. We heard them. We detected gravitational waves. Imagine dropping a bowling ball onto a trampoline. The trampoline distorts, creating ripples that spread outwards. Now, imagine two black holes, millions of light years away, spiraling into each other, accelerating to incredible speeds, and finally, smashing together in an event that releases more energy than all the stars in the observable universe combined. For a fleeting fraction of a second, this cataclysmic collision sends ripples through the very fabric of space-time itself, like the bowling ball on the trampoline. These ripples, these gravitational waves, are what we heard. Our detectors, LIGO and Virgo, are so sensitive they can measure distortions in space-time smaller than the width of an atom's nucleus. When those black holes merged, they created a chirp, a subtle rising frequency that lasted mere milliseconds. It was the universe singing, a primordial echo of its most violent, most powerful acts. It was the confirmation of Einstein's century-old predictions, and it opened a whole new window into the cosmos. We're not just seeing the universe anymore. We're listening to it. We're hearing the echoes of giants. These cosmic engines, neutron stars, pulsars, and black holes, are not just wonders. They are silent, powerful characters in the cosmic drama. They are the ultimate destroyers, the ultimate shapers. They remind us that the universe is not a gentle place. It's a realm of unimaginable power, where life, if it exists elsewhere, must contend with forces that rip apart stars, swallow light, and warp the very fabric of reality. They are the silent watchers, not actively malicious, but simply existing. Their very presence, a testament to the universe's raw, untamed power. And their existence, their omnipresence throughout the cosmos, makes us wonder again about that profound silence we've encountered. If the universe is brimming with such destructive power, if these cosmic giants are lurking in the shadows of every galaxy, then what does that say about the nature of survival for any intelligent civilization that might emerge? What if the silence isn't because no one else is out there? What if the silence is a deliberate choice? What if, in a universe filled with such incomprehensible forces, the greatest wisdom isn't to shout your presence, but to remain utterly, profoundly, terrifyingly silent? But what if that silence isn't a choice at all? What if the universe itself, in its grand, indifferent wisdom, is simply keeping a secret so fundamental, so deeply woven into the fabric of reality, that it dictates everything we see, everything we are, yet remains utterly, profoundly, terrifyingly silent to our instruments, To our very senses, for all our telescopes, all our incredible science, we've come to a humbling realization. The universe we see, the stars, the galaxies, the planets, us, it's just a tiny shining speck. A cosmic illusion, perhaps, because the vast majority of everything out there, the real architects of the cosmos, are completely maddeningly invisible. They are the unseen hands, shaping destiny from the shadows. And they are, quite literally, dark. Imagine a giant cosmic merry-go-round. You'd expect the stuff in the middle, the dense core, to spin faster than the stuff on the edges, right? That's how it works, with planets orbiting a star, or kids on a playground ride. The closer you are to the center, the faster you need to go. To stay in orbit makes sense. But then, in the 1970s, a brilliant astronomer named Vera Rubin started looking at galaxies, not just one or two, but dozens. And what she saw was impossible. The stars on the very outer edges of these colossal pinwheels were spinning just as fast, sometimes faster, than the stars closer to the galactic core. It was like watching a car race, where the cars on the outside lane were keeping pace with the cars on the inside. Without flying off the track, this defied everything we thought we knew about gravity. There simply wasn't enough visible matter, the stars, the gas, the dust, to generate the gravitational pull needed to hold those outer stars in place. They should have been flung out into the cold, empty void of intergalactic space millions of years ago. But they weren't. They were still there, locked in their impossibly fast dance. Vera Rubin, a quiet force of nature who battled sexism in the scientific community just to get her observations taken seriously, had stumbled upon one of the universe's greatest mysteries. There had to be something else, something invisible, providing the extra gravitational muscle. Something dark. And that, my friends, is how we first encountered the ghost in the machine. Dark matter. It's not dark in the way a black hole is dark, sucking in light. It's dark because it doesn't interact with light at all. It doesn't absorb it, reflect it, or emit it. It's truly invisible. And it's not made of the stuff you and I are made of. Protons, neutrons, electrons. That's baryonic matter. And it's what makes up everything we've ever touched, seen, or smelled. Dark matter is something else entirely. Something exotic. Something profoundly alien. Think of it this way. Our entire universe, the one we perceive with our senses and our most powerful telescopes, is like a gorgeous, intricate tapestry. But what if that tapestry is actually just the embroidery? And beneath it, holding all the threads in place, giving it its shape and structure, is an enormous, invisible sheer fabric. That fabric, my friends, is dark matter. It's the cosmic scaffolding, the gravitational glue that holds galaxies together, stopping them from flying apart at their impossible speeds. Rubin's observations were just the beginning. The evidence for dark matter has piled up like cosmic building blocks ever since. One of the most stunning examples comes from something called gravitational lensing. Einstein, brilliant as he was, predicted that massive objects would warp space-time, bending light that passes near them. It's like looking through a funhouse mirror, where distant galaxies get stretched and distorted. And when we look at colossal galaxy clusters, we see way more lensing than the visible matter could possibly cause. It's as if there's an enormous invisible mass acting as a super lens, bending light that isn't even touching anything we can see. The most famous example, the Bullet Cluster. Picture two galaxy clusters, each a behemoth in its own right, slamming into each other at millions of miles per hour. When they collided, the normal visible gas clouds, which make up most of the ordinary matter, got heated up and slowed down, forming a shock wave. But the dark matter in those clusters, which doesn't interact with itself, just sailed right through each other, like ghosts passing through walls. We can see the gas, glowing in X-rays, but we can map the dark matter by how it bends light, and what we find are two distinct ghost clumps that pass straight through the collision. It's like watching a magic trick, where the magician's hidden assistant is finally revealed by the way the stage curtains move around them. Then there's the cosmic microwave background, the faint afterglow of the Big Bang. It's a snapshot of the universe when it was just a baby, only 380,000 years old. And the tiny temperature fluctuations in that background radiation, they tell us an incredible story about the initial seeds of structure. Without dark matter, those tiny fluctuations simply wouldn't have had enough gravitational oomph to grow into the colossal galaxies and galaxy clusters we see today. It's the initial whisper that grew into the cosmic roar. This brings us to one of the most breathtaking visions of our universe, the cosmic web. Imagine the universe not as a uniform, bland soup, but as a vast, interconnected network, like a gigantic, glowing spider web, spanning billions of light years. Or perhaps a cosmic neural network, pulsing with unseen energy. At the intersections of this web, where the filaments converge, are the richest galaxy clusters. Along the strands, galaxies string together like pearls on a necklace. And in the vast, empty spaces between the strands, those are the cosmic voids, regions almost entirely devoid of galaxies, of light, of ordinary matter. This incredible structure, this cosmic architecture, is almost entirely sculpted by dark matter. It's the gravitational scaffolding that pulls ordinary matter together, creating the superhighways and megacities of the universe. Without dark matter, gravity simply wouldn't be strong enough to overcome the universe's expansion and form these large-scale structures. The universe would be a much more uniform, much less interesting place. It'd be like trying to build a skyscraper without any steel girders, just brick and mortar. So we have dark matter, the invisible glue holding things together. You'd think that's the biggest mystery, right? We've accounted for the missing gravity, explained the spinning galaxies, the cosmic web. Case closed? Not even close. Because just as scientists were getting a handle on dark matter, another, even more profound enigma burst onto the scene, shattering our understanding of the universe's ultimate fate. For decades, we thought the universe's expansion, set in motion by the Big Bang, was gradually slowing down, like a ball thrown into the air. We expected gravity, from all the matter and dark matter, to be pulling everything back, even if slowly. But in the late 1990s, two independent teams of astronomers studying distant supernovae, exploding stars so bright they can be seen across billions of light years, made an absolutely jaw-dropping discovery. The universe wasn't just expanding, it wasn't even slowing down, it was accelerating, getting faster and faster, every single second. Imagine throwing that ball into the air, and instead of slowing down, it just kept picking up speed, rocketing away into the sky. That's what we found the universe was doing. And it was a wow moment that earned a Nobel Prize. Some mysterious force, was pushing the universe apart, overcoming gravity itself. Something we now call dark energy. If dark matter is the unseen hand that builds the cosmic web, then dark energy is the unseen hand that's tearing it apart. It's even more mysterious than dark matter. We don't even have a good theoretical candidate for what it might be. Is it a property of empty space itself, a kind of cosmic anti-gravity, a new fundamental force? We genuinely don't know. Think of it like this. Picture the universe as a giant loaf of raisin bread baking in an oven. As the bread rises, the raisins, galaxies, move further apart. That's the expansion. Now imagine that as the bread rises, some invisible force is making the dough itself expand faster and faster, constantly adding more space between the raisins. That's dark energy. It's not pushing on the galaxies, it's pushing on the space between them. It's a pervasive, uniform pressure that exists everywhere, constantly creating more space, stretching the fabric of the cosmos. And here's the kicker. This invisible, mysterious stuff, dark energy, makes up about 68% of the entire universe. Add that to dark matter's 27%, and you're left with a staggering truth. All the stars, all the planets, all the galaxies, all the cosmic wonders we've marveled at, all the ordinary matter that makes up us, it accounts for less than 5% of everything. 5%. We are quite literally living in a universe dominated by forces we cannot see, cannot touch, and barely understand. This realization, this profound cosmic humility, has ignited one of the most intense scientific quests in history. Scientists around the world, from quiet university labs to massive international collaborations, are dedicating their lives to chasing these ghosts. They're building underground detectors, shielded from cosmic rays, hoping to catch the faintest whisper of a dark matter particle colliding with a regular atom. They're launching sophisticated space telescopes, like the upcoming Euclid mission, to precisely map the cosmic web and the distribution of dark matter and dark energy across billions of light years. Imagine the frustration, the sheer tenacity of these researchers. Years, sometimes decades, of work, hunting for something that by its very nature refuses to interact with anything we know. It's like trying to find a shadow in a pitch-black room or listening for a whisper in the middle of a supernova explosion. The failures are frequent, the breakthroughs agonizingly slow. But the hope of cracking this cosmic code, of understanding the true nature of 95% of our universe, that's what keeps them going. It's a testament to the human spirit, isn't it? To face such overwhelming ignorance, such a colossal mystery, and to say, we will understand. We must understand. We're not just looking for particles. We're looking for answers to the most fundamental questions about existence itself. What is reality made of? What is our place in it? And what does it mean that the universe is so profoundly, overwhelmingly dark? So, if dark matter is the unseen architect, building the cosmic web, and dark energy is the relentless expander, pushing everything apart, what does that mean for the ultimate fate of our universe? Well, if dark energy continues its dominance, if it keeps accelerating the expansion, then the universe faces a truly chilling future. Galaxies will continue to rush away from each other, faster and faster, until eventually they'll recede beyond our cosmic horizon. The light from distant galaxies will become so stretched, so redshifted, that it will simply fade away. Our local group of galaxies, the Milky Way and Andromeda, might remain gravitationally bound, but beyond that, the night sky will become utterly, profoundly empty. A vast, cold, lonely void. The cosmic web, once vibrant with light, will stretch thin, its filaments snapping. It's a future where the universe grows so vast, so diffuse, that even the fundamental particles themselves might eventually be ripped apart in what scientists chillingly call the Big Rip. Or perhaps it's a big freeze, where everything just expands into eternal coldness, an ultimate state of cosmic loneliness, and it leaves us with an even deeper question, doesn't it? If 95% of our universe is invisible, unknowable, a silent force dictating our reality, what other profound secrets are still lurking in the cosmic shadows? What other unseen hands are at play, shaping our destiny? Or perhaps the destiny of other civilizations we're so desperately trying to find? We've searched the stars for answers, for companionship, for a signal. But perhaps the greatest mystery, the most terrifying truth, isn't out there in the form of an alien message, but right here, woven into the very fabric of existence itself. A reality where the universe is mostly silent, not because it's empty, but because its deepest truths are simply beyond our current comprehension. And as we continue to reach out, to listen, to probe the dark, we have to wonder, what else will we find that forces us to redefine everything we thought we knew? What other fundamental components of reality are waiting to emerge from the profound, terrifying silence of the cosmos? That silence, that profound, echoing emptiness, it's been a constant companion on humanity's journey through the universe. For decades now, we've flung our messages out into the cosmic ocean, a beacon in the night. We've broadcast our hopes, our dreams, our very existence, like a message in a bottle cast out from a lonely island. Think about the Arecibo message, beaming our story, our DNA, our place in the solar system, toward the M13 globular cluster. A cosmic hello, sent hurtling through the void at the speed of light. But if you listen closely, not just to the static, but to the lack of anything else, it's deafening, isn't it? We've expected a reply. We've hoped for a reply. But all we've ever received is an eerie, unsettling quiet. The kind of quiet that makes the hairs on your arms stand up when you're alone in a dark house. It's the ultimate cosmic contradiction. On one hand, you've got a universe that's impossibly vast, a canvas stretching billions of light years, dotted with trillions of galaxies, each home to hundreds of billions of stars. And around so many of those stars, we now know, are planets. So many planets, some of them Earth-like, bathed in the warmth of their suns, swirling with the chemical ingredients for life. We're talking about numbers so staggering, they almost lose meaning. More stars than grains of sand on all the beaches of Earth. More potential homes for life than we can possibly imagine. So, here's the question that keeps brilliant minds up at night, that haunts every single one of us who gazes up at the night sky. If the universe is so gargantuan, so incredibly fertile, so ripe with possibility, then where is everybody? Where are the lights? Where are the signals? Why aren't our cosmic radios buzzing with the chatter of countless civilizations? This, my friends, is the Fermi Paradox, and it's arguably the most profound, most unsettling question humanity has ever asked itself. The physicist Enrico Fermi, a man whose genius helped usher in the atomic age, famously posed it during a casual lunch in 1950. He looked around, thought about the sheer probability of life evolving elsewhere, and simply asked Monier Theoretor, but where are they? So, what are the answers? Scientists, philosophers, and dreamers have wrestled with this for decades, proposing solutions that range from the deeply comforting to the utterly terrifying. Let's start with one of the most sobering ideas, the Great Filter. Imagine a series of cosmic hurdles, incredibly difficult, perhaps even impossible, for life to overcome on its path to becoming a spacefaring civilization. This Great Filter could be behind us, in our past, maybe the very origin of life, abiogenesis, the leap from inert chemistry to self-replicating organisms, is so monumentally improbable that it's happened only once, here on Earth. Think about it. The precise dance of molecules, the spark of the energy, the perfect environmental conditions all coming together, not just to create life, but to create complex life. Maybe that's the bottleneck. We've already passed it. We're the lucky ones, the cosmic lottery winners. Or perhaps the filter was the evolution of complex multicellular life. For billions of years on Earth, life was just single-celled organisms, microscopic blobs bumping around. It took an incredibly long time, and a confluence of geological and atmospheric events for something more intricate to emerge. Maybe that jump is the real rarity. What if consciousness itself is the filter? The ability to reason, to innovate, to build tools, to dream of the stars. It's an extraordinary leap from instinct to intellect. We take it for granted, but maybe it's an evolutionary path, so narrow, so precarious, that very few species ever navigate it. If any of these early filters are the answer, it means we're incredibly special, incredibly rare. We've overcome the odds. And that thought, while a little lonely, is also profoundly reassuring. We're the exception now. But then there's the other, far more chilling possibility. What if the great filter is ahead of us? What if the biggest hurdle, the insurmountable obstacle, is yet to come? This is where the existential dread really starts to set in. If the filter is in our future, it means that almost every civilization that reaches our level of technological advancement, or just beyond it, inevitably hits a wall. And that wall, it's usually self-destruction. Imagine a civilization that develops the power to split the atom, to unleash unimaginable energies. They also develop weapons capable of wiping themselves off the map, or they burn through their planet's resources, pollute their atmosphere, trigger runaway climate change, and collapse under the weight of their own consumption. Or maybe they create an artificial intelligence so powerful it decides humanity is obsolete. It's a grim mirror, isn't it? Every time we look at our own global challenges, climate change, nuclear proliferation, pandemics, even the ethical dilemmas of AI, we have to ask ourselves, is this it? Is this our filter? Are we destined to join the silent ranks of countless other civilizations who reached for the stars, only to fall back into the dust of their own making? The thought is enough to make any scientist, any rational human being, feel a deep, cold knot of fear in their stomach. Because if this is true, then the universe isn't silent because life is rare, but because intelligent life is doomed. Of course, there are less apocalyptic possibilities. Maybe they're just too far away. The sheer scale of the universe is almost impossible to truly grasp. If you could travel at the speed of light, the fastest thing in the universe, it would still take you 2.5 million years to reach our nearest galactic neighbor, Andromeda. Would humanity even exist by the time you got there? And that's our neighbor. Most of the universe is billions of light years away. Even if civilizations are out there, even if they're sending signals, those signals might simply take too long to reach us, or they've already passed us by, arriving from a civilization that's long since turned to cosmic dust. The universe is a vast, ancient place, and we are but a brief flicker in its timeline. Or perhaps they're simply too alien. We tend to imagine aliens as variations of ourselves, bipedal, carbon-based, communicating with radio waves. But what if a truly advanced civilization has moved beyond biological forms entirely? What if they've uploaded their consciousness into vast, planet-sized supercomputers, existing in dimensions we can't even perceive? What if they communicate using quantum entanglement or manipulate space-time in ways we can only dream of? For them, our radio signals would be like cave paintings, too primitive to even register as intelligent communication. They wouldn't be silent. We'd simply be deaf to their existence. Imagine a civilization that has transcended the need for a physical body, or even a single planet. We talk about the Kardashev scale, a way to classify civilizations by their energy consumption. A Type I civilization could harness all the energy of its home planet. A Type II could control the entire output of its star, perhaps building a Dyson sphere around it. A Type III? They'd command the energy of an entire galaxy. If such civilizations exist, they wouldn't just be advanced. They'd be utterly incomprehensible to us. Their motivations, their priorities, their very existence might be so far removed from our own that we wouldn't even recognize them as life, let alone as a civilization. They might be right here, all around us, invisible, because we lack the senses, the technology, or even the conceptual framework to perceive them. But let's return to that initial, chilling observation. The silence. The Arecibo message, our cosmic hello, still hurtling outward. What if that act, that simple broadcast of our existence, is the most dangerous thing we could possibly do? This brings us to perhaps the most terrifying answer to the Fermi Paradox, a concept that feels less like science and more like a cosmic horror story. The dark forest theory. Imagine the universe not as a bustling cosmic metropolis, but as a vast, ancient, and very dark forest. Every civilization in this forest is a hunter. They move silently, stealthily, camouflaged in the shadows. Each carries a weapon, and each knows that if they expose their location, if they make a sound, if they show any sign of their presence, they become prey. The other hunters, those we can't see, will immediately try to eliminate them. Not out of malice, necessarily, but out of pure cold logic. Any other intelligent life form is a potential threat, a competitor for resources, a future aggressor. The safest course of action, the ultimate act of self-preservation, is preemptive strike. Silence is survival. Exposure is annihilation. Think about it. We've been broadcasting our presence, loudly and proudly, into this cosmic dark for almost a century. We've sent out radio waves from our televisions, our radar, our very first broadcasts, proclaiming Yerfyo, here we are. If the dark forest theory holds any truth, if the universe truly operates under these brutal, unforgiving rules, then our Arecibo message, our Voyager golden records, our every radio signal seeping out into the cosmos, they aren't acts of hopeful exploration. They are the equivalent of a naive child, wandering into a jungle teeming with apex predators, shining a flashlight on themselves and shouting, "Rule! Hello, I'm over here." By announcing our presence, by yelling into the dark, we might not be inviting friendship. We might be inviting something far, far worse. So, as we continue to listen, to search for those elusive signals, to send out our own desperate plea for contact, we have to ask ourselves, what if the greatest danger isn't that we don't find anyone? What if the real terror is that someone, somewhere, has already heard us? And what if their answer is not a friendly wave, but a silent, unseen journey across the void, aimed directly at the little blue planet that dared to make a sound? The universe is silent, but is it the silence of emptiness, or the terrifying quiet of a predator holding its breath, waiting for you to make the first move? The answer to that question might be the most important and the most frightening truth we ever uncover. And it might be coming for us, faster than we think. The universe is silent, but is it the silence of emptiness, or the terrifying quiet of a predator holding its breath, waiting for you to make the first move? The answer to that question might be the most important and the most frightening truth we ever uncover. And it might be coming for us, faster than we think. For decades, we've been shouting into the cosmic void. Take the Arecibo message from 1974. A simple radio signal, packed with information about who we are, where we live, our DNA, our very existence. It was a cosmic handshake, a hopeful greeting launched from a giant dish in Puerto Rico, hurtling towards a star cluster 25,000 light-years away. We've sent others too. Our television and radio waves have been leaking into space for over a century, a growing bubble of human noise expanding across the galaxy at the speed of light. It's our interstellar billboard announcing, "Hey, we're here. Come say hello." But here's the thing that keeps astronomers up at night, staring at the ceiling of a universe that seems to be doing the exact opposite of saying hello. Nobody's answered. Not a peep. Not a whisper. Just silence. This isn't just awkward. It's profoundly unsettling. Because by all accounts, the universe should be teeming with life. There are billions of galaxies, each with hundreds of billions of stars. Many of those stars have planets, and a good chunk of those planets are in the Goldilocks zone. Not too hot, not too cold, just right for liquid water. With quadrillions of potential homes out there, even if life is rare, even if intelligent life is rarer still, the sheer numbers suggest that our galaxy alone should have hundreds, if not thousands, of advanced civilizations. This is the heart of the Fermi Paradox. If they're all out there, where is everybody? Why aren't there signals flooding our receivers? Why haven't their probes visited? Why haven't they left their cosmic litter all over the place? It's a question that's haunted us for generations, leading to all sorts of theories, from the Great Filter, some cosmic hurdle that nearly all life fails to overcome, to the idea that maybe they're just too far away, or not interested, or perhaps we're just looking in the wrong places. But what if the silence isn't an absence of life? What if it's a deliberate choice? What if the quiet isn't because there's nobody out there, but because everyone out there knows better than to make sound? Imagine the universe not as a friendly neighborhood or a vast, empty expanse, but as a vast, ancient, and very, very dark forest. Every civilization in this forest is a hunter. Each one is armed, and each one is terrified, because in this dark forest, there's an ironclad rule. If you expose yourself, if you make a sound, if you reveal your position, you will be eliminated, immediately, silently, without mercy. This is the dark forest theory, first popularized by Chinese author Liu Cixin in his mind-bending science fiction series. It's not just a story. It's a chillingly logical, brutally efficient answer to Fermi's paradox. Think about it. Any civilization, upon achieving interstellar travel or communication, faces an existential dilemma. What are the intentions of other civilizations? We can't know. They could be benevolent, or they could be hostile. And because the distances between stars are so vast, so mind-bogglingly immense, any direct contact, any negotiation, any attempt to understand would take centuries, millennia. Communication delays are civilization-killing delays. If a threat is detected, by the time you've sent a message, gotten a response, and decided on a course of action, it would already be too late. The only logical, safe course of action, from an alien civilization's perspective, is to assume the worst, to assume every other life form is a potential threat, a competitor for finite resources, an existential danger to your own species' survival. So, you don't wait. You don't ask questions. You don't risk interaction. You eliminate the threat, on sight, or more accurately, on signal. The universe becomes a game of cosmic hide-and-seek, but with truly terrifying stakes. Every advanced civilization becomes a master of stealth, a silent predator, or a silent prey. They listen, always listening, for any flicker of light, any whisper of a signal, any sign that another hunter has revealed itself. And when one does, when a civilization like ours makes the rookie mistake of broadcasting its presence, of shining a flashlight into the darkest corner of the forest, then the other hunters are forced to act, not out of malice necessarily, but out of self-preservation. Because if they don't eliminate the exposed civilization, who's to say that exposed civilization won't eliminate them first? It's a cosmic arms race, a zero-sum game played out across unimaginable distances, where the best defense is a swift, silent, and utterly complete offense. It's a terrifyingly elegant solution to the paradox, isn't it? The reason we haven't heard from anyone isn't because they don't exist. It's because they're all too busy hiding. Or perhaps, too busy hunting. Let's imagine it for a moment. Picture a world, millions of light years from Earth. We'll call it Xylos. It's a stunning sapphire jewel, orbiting a binary star system, bathed in the gentle glow of two suns. For billions of years, life has flourished there. Its oceans teem with bioluminescent creatures, its continents are covered in forests of colossal, crystalline flora, and its skies are crisscrossed by the shimmering aerial cities of a civilization that has mastered its world. They've built wonders, solved mysteries, advanced beyond our wildest dreams. They've even begun to send out their own signals, their own hopeful greetings, just like we have. Perhaps a few thousand years ago. They're a vibrant, thriving testament to the universe's potential. Then, one day, from a distant corner of their galaxy, an event, not an explosion, not a war, just a flicker, a pinprick of light, too faint for the naked eye, but picked up by their advanced telescopic arrays, a concentrated beam of energy, traveling at near light speed, unleashed from an unseen source, light years away. It carries no fanfare, no warning. It's just physics, a weapon designed for ultimate efficiency. It slices through the vacuum of space, through Xylos's atmosphere, through its shimmering cities, its crystalline forests, its bioluminescent oceans. The beam doesn't just destroy, it incinerates, it ionizes, it vaporizes. In a cosmic heartbeat, a world that once pulsed with life, with ambition, with hope, is reduced to a cloud of superheated plasma and vaporized dust. A beautiful, vibrant planet, gone, utterly, irrevocably annihilated. And the silence returns, a profound, absolute silence, stretching across the vast gulfs of space where Xylos once spun. Perhaps another civilization, in another galaxy, met a similar fate. A world of intelligent, empathetic beings who had just begun to harness the energy of their star, dreaming of cosmic exploration. Perhaps they sent out a beacon, a message of peace and curiosity, filled with beautiful music and mathematical proofs. And perhaps that signal, traveling at the speed of light, eventually reached the ears of a silent hunter, billions of years more ancient, billions of years more paranoid. A hunter who, without a moment's hesitation, without a second thought, dispatched a relativistic kinetic weapon, a tiny, undetectable projectile, moving so fast it carries the destructive power of a supernova, and simply erased them. No battle, no negotiation, just a cold, logical removal of a potential threat. And the silence deepened. This scenario, repeated countless times across the eons, across the unfathomable expanse of the cosmos, paints a chilling picture. The reason we see no signs of life, no bustling galactic empires, no alien megastructures, isn't because the universe is empty. It's because the universe is a battlefield, where the only way to survive is to never, ever be seen, to embrace the deep, cold, terrifying silence. So, where does that leave us, humanity? With our radio telescopes pointed at the stars, our television signals leaking into the void, our Arecibo message still cruising through the cosmic currents. We've been screaming our presence into the dark forest for a century. We've painted a giant target on our backs, inviting, well, we don't know what we're inviting. But if the dark forest theory holds true, then our cosmic innocence, our eager desire to connect, our hopeful broadcast of our existence, could be the ultimate act of self-sabotage, our greatest vulnerability. This isn't just science fiction anymore. It's a profound philosophical question that demands we reconsider everything we thought we knew about our place in the universe. Do we continue to listen? Do we continue to broadcast? Or do we, for the first time, truly understand the wisdom of silence. The implications are staggering. It forces us to confront not just the potential for alien life, but the potential for alien motivations. Motivations driven by ancient fears, by the absolute logic of survival, by the cosmic imperative to eliminate all potential threats. We look up at the night sky, and we see billions of stars, each a sun, many with planets. We still send our signals, still hope for a reply. But now, that hope is tinged with a new icy dread. Because the silence isn't just a lack of communication. It's a warning. It's the sound of every other civilization out there, holding its breath, waiting. And as our own radio waves continue to expand, a growing sphere of human noise, announcing our presence to the unknown, we have to ask ourselves, by shouting into the universe, are we introducing ourselves to friends? Or are we, in our desperate yearning for connection, simply pointing out the prey to the hunters lurking in the terrifying, unforgiving depths of the cosmic dark forest? The answer might already be on its way.